I'm using CalibratedClassifierCV to fix a problem with my support vector machine, SVM. My SVM, which I'm using for binary classification, isn't giving me well-calibrated probabilities. That means the probabilities it predicts don't accurately reflect the real chances of something belonging to the positive class. Therefore, I need CalibratedClassifierCV to improve things. It's a tool that helps make predictions more reliable. My SVM model is giving me poorly calibrated probabilities. This means the model's predicted probabilities of an instance belonging to the positive class don't match the actual frequency of positive instances. For example, if the model predicts a 70% probability, I shouldn't see approximately 70% of those instances being actually positive. This lack of calibration makes the predictions less reliable. I'm using CalibratedClassifierCV to solve the poorly calibrated probabilities problem. This is a scikit-learn tool designed to adjust the predicted probabilities of a classifier, making them more accurate representations of the true probabilities. It's like a calibrator for my predictions. I think that CalibratedClassifierCV won't directly improve my SVM's accuracy. Accuracy is about correctly classifying instances, and calibration focuses on making the predicted probabilities more reliable. While better calibrated probabilities might indirectly help accuracy, for example, by aiding in setting better thresholds for classification, it's not a guaranteed outcome. Yes. CalibratedClassifierCV offers different ways to calibrate probabilities. Sigmoid and isotonic are two examples. The sigmoid method uses a sigmoid function to transform the probabilities. The isotonic method creates a non-decreasing calibration curve. This flexibility helps me find the best method for my data. I don't expect CalibratedClassifierCV to always improve the area under the curve, AUC, score. The AUC measures how well a model ranks instances, not its probability calibration. Calibration primarily affects the predicted probabilities, so the ranking might not be significantly altered. An AUC score might even slightly decrease while probability calibration improves. Correct. CalibratedClassifierCV adds extra computational work because it trains another model on top of the original SVM. The extra computational cost will depend on factors such as the size of the dataset and which calibration method I choose. I'm starting with an SVM, support vector machine, a powerful classification algorithm, but its predicted probabilities aren't reliable. They don't accurately reflect the true likelihood of a data point belonging to the positive class. Think of it like a weather forecast that says there's a 70% chance of rain, but it rains only 30% of the time when the forecast predicts 70%. To fix the unreliable probabilities from my SVM, I'm using CalibratedClassifierCV. It's a tool from scikit-learn that takes my existing SVM and makes its probability predictions more accurate. It does this by training a secondary model to calibrate the probabilities. Think of it as a calibration tool for my SVM's probability predictions. Before using CalibratedClassifierCV, my SVM gives probabilities that are not trustworthy. For example, a prediction of 0.8 might actually correspond to an only 60% chance of the positive class. These are poorly calibrated probabilities. After using CalibratedClassifierCV, the probabilities from my SVM are much better. A prediction of 0.8 now is much closer to actually meaning there's an 80% chance of the positive class. These are well-calibrated probabilities. CalibratedClassifierCV offers different ways to do its calibration. Two popular methods are sigmoid, flat scaling, and isotonic regression. I can choose which one best suits my data. Each method uses a different approach for adjusting my SVM's predictions to be more accurate. It's like having two different tools in my toolbox. This means my SVM model is giving probability predictions that don't accurately reflect the real-world chances of something happening. For example, if the model predicts a 70% probability of something, it might not actually happen 70% of the time in reality. This is the problem we're trying to fix. I'll use CalibratedClassifierCV, a scikit-learn tool, to improve this. It's like a wrapper that takes my existing SVM model and makes its probability predictions more accurate. Think of it as a probability calibration expert. While better calibrated probabilities might indirectly help, this tool focuses on making probabilities more reliable, not necessarily improving the model's overall accuracy directly. I might not see a big improvement in the number of correct predictions. That's correct. CalibratedClassifierCV offers choices. I can use different methods, like sigmoid, a smooth curve approach, or isotonic, a more flexible approach that adapts better to non-smooth data, to adjust the probabilities to match reality better. This is its strength, letting me tailor it to my needs. AUC, area under the ROC curve, measures how well a model ranks instances, not just probabilities. Improving calibration does not always improve the ranking, therefore it does not improve AUC. The ranking of possibilities might not change even with better calibrated probabilities. Yes, CalibratedClassifierCV adds extra work. It trains a second model to adjust the initial SVM's probabilities. This makes it slower, especially with large datasets. This trade-off between speed and better calibration is something to keep in mind. I start with a support vector machine, SVM, that's not doing a great job of predicting probabilities. Its predictions are unreliable. A predicted probability of 0.8 might not actually mean an 80% chance of the event happening. I use scikit-learn's _CalibratedClassifierCV to fix this. This tool takes my unreliable SVM and makes its probability predictions more accurate. Think of it as a probability calibration tool, refining the raw predictions from the SVM. _CalibratedClassifierCV is a type of meta-estimator. It uses another model to improve the predictions of an existing model. In this case, the existing model is the SVM. It helps adjust the SVM's predicted probabilities to better match reality. _CalibratedClassifierCV offers different methods, to improve the probabilities. Two common methods are sigmoid, which uses a sigmoid function to map the SVM's scores to probabilities, and isotonic, which creates a more complex calibration curve. I choose the method best suited to the problem I'm facing. My initial SVM is producing probabilities that aren't trustworthy. For example, if it predicts a 70% chance of an event, it doesn't necessarily mean that the event will happen 70% of the time. This is what we mean by poorly calibrated probabilities. After using _CalibratedClassifierCV, I'll get probabilities that are closer to the actual frequency. A predicted 70% would now more likely reflect a true 70% chance of the event. Using _CalibratedClassifierCV is like giving the SVM a second chance, a refinement pass to improve the reliability of its probability predictions. It doesn't magically improve accuracy, it refines the calibration of the model's probabilities. I start with a support vector machine, SVM, model. It's a powerful classification tool, but its probability predictions are inaccurate. Think of it like a weather forecaster who says there's a 70% chance of rain, but it only rains about 40% of the time when they make that prediction. This inaccuracy is called poor calibration. I use CalibratedClassifierCV, a scikit-learn tool. It's like a probability prediction improving machine. It takes my poorly calibrated SVM and makes its predictions more accurate, more believable. It does this by training another model on top of the original SVM to refine those probability outputs. I have choices here. CalibratedClassifierCV offers different ways to adjust the probabilities. Sigmoid uses a simple curve to fine-tune them. Isotonic is a more sophisticated, flexible approach that adapts to the data more intricately. These are the probabilities my original SVM gives me before I use CalibratedClassifierCV. They are not reliable because they don't accurately reflect how often the positive class actually occurs. After using CalibratedClassifierCV, I get these. These are much more accurate representations of the true probability of the positive class. My predictions are significantly improved. I first train an SVM model. Then, I notice the calibration problem. The probability outputs are inconsistent with observed frequencies. I then use the CalibratedClassifierCV function from Sklearn, selecting a calibration method, sigmoid or isotonic. This creates a new model based on the initial SVM model's output and improves probability predictions. I see an SVM, a powerful tool for classification, but its probability predictions aren't reliable. That means a predicted probability of, say, 80% doesn't accurately reflect a true 80% chance of belonging to that class. This is what we need to fix. This is a Sklearn tool. I use it to take an existing classifier, like our unreliable SVM, and improve its probability predictions, ensuring they match the actual class proportions better. Think of it as recalibrating a somewhat inaccurate scale. After I use _CalibratedClassifierCV, I'll get a better SVM. Its probability estimates will be much closer to reality. I have options. CalibratedClassifierCV isn't a one-size-fits-all solution. I can choose different methods, like sigmoid, Platt scaling, or isotonic regression, to find the best approach for my specific data. It's like having different tools for adjusting the scale, each suited for different situations. There's a trade-off. Using _CalibratedClassifierCV adds extra computation because I'm essentially training a secondary model on top of the SVM. So, it will take longer to run. The added time will depend on data size and the calibration method I select. It's like paying a small price for a better calibrated outcome. One of the methods I can use is sigmoid, which uses a sigmoid function to transform the predicted scores into probabilities. It's like applying a smooth curve to improve the calibration. Another calibration method. It finds the optimal mapping of the SVM's scores to probabilities using a non-parametric regression technique. I might choose this over sigmoid based on the data. Think of it as using a more flexible, data-driven adjustment instead of a predefined curve. I choose a calibration method. Sklearn's CalibratedClassifierCV offers two main options. Sigmoid, which uses Platt scaling, a logistic regression model to adjust probabilities, and isotonic, which employs isotonic regression, a non-parametric method. I select the one that's likely to best fit my data. I start with my SVM model's predictions. These are uncalibrated probabilities, meaning they don't accurately reflect the true likelihood of a positive outcome. They're the raw output from my SVM before any calibration happens. With my chosen method, I train a secondary model, either a logistic regression model, for sigmoid, or an isotonic regression model, to adjust these probabilities. This new model learns the mapping between the SVM's raw probabilities and the observed frequencies of the positive class in my training data. After training, I get adjusted probabilities from this secondary model. These are my calibrated probabilities, hopefully better reflecting the true positive class probabilities. My final output are these improved, calibrated predictions. I can now use these to make classifications with more confidence, because they're a more accurate reflection of the probabilities. I visualize the whole process as a pipeline. First, I feed my uncalibrated SVM predictions into the CalibratedClassifierCV. Then, I select a calibration method. Then, a calibration model is trained and applied to produce final calibrated predictions.